So welcome to lecture 2. And okay, so last time we introduced like the very basic concepts of propositional logic. So we introduced propositions. Proposition was just a statement that's either true or false, but not both. We talked about logical operators, namely not, or, and, as well as some things you could derive from those, such as conditionals, biconditionals, etc. And we talked about when compound propositions are equivalent. And today, what we're going to do is we're going to do 3 things. So we're going to continue talking about, we're going to briefly wrap up equivalence of compound propositions, so logical equivalence. And then we're going to greatly enhance this language to talk about collections of objects by introducing propositional functions and quantifiers. And then finally, we're going to talk about rules of inference, which are basically ways of combining propositions that you know to get new propositions. And that's ultimately how mathematics is done. So roughly, this is how to build or how to deduce. Well, I'll say what it is later. So let me begin by talking about this. So recall that I said 2 compound propositions, let's say C1 and C2 are logically equivalent if they both have the same truth value. Regardless of the truth values of the constituent of the propositional variables, for all values of propositional variables. And one sort of cute remark is that this notion of equivalence of 2 compound propositions can itself be written as a proposition. So C1 is equivalent to C2 is the same as saying that C1, if and only if C2 is always true. So it is equivalent to the proposition true. And this type of situation has a special name, and we're going to see it a lot in the course. This is called a tautology. So let me just so let me just introduce a small piece of terminology. Compound proposition C is a tautology if it's always true. So it's logically equivalent to true. So it doesn't matter what the propositional variables are, it's always true. For example, the proposition P implies Q if and only if not Q implies not P. So that's always true regardless of the truth values of P and Q. That's saying that the conditional is logically equivalent to the contrapositive. And we'll say that a compound proposition is a contradiction if it's logically equivalent to false. So can anybody think of a propositional variable, compound proposition that's a contradiction?
Like P and not P?
Yeah, P and not P, that's the simplest one. And otherwise it's called contingent. And you can think about these three cases in terms of their truth tables, right? A tautology has the property that all the rows in its truth table are T. They're all true. A contradiction, all the rows are false. And a proposition is contingent if some of the rows are true and some of them are false. So tautologies seem like kind of a boring thing, right? Like, well, if it's always true, then what's the point, right? It doesn't sound very interesting. But tautologies can actually capture interesting, well, patterns of reasoning. So here are some examples of some easy but interesting tautologies. So,
Wait, sorry, could you scroll up for a second? Because I think you cut off like part of the bottom, so I couldn't see all of the notes. No, like the bottom row, I can't see it for some reason. I don't know why.
oh, you can't see the bottom row. Okay.
Yeah, so I can only see up to contradiction, and then I can't see anything else below.
Oh,
Oh wait, never mind. I
okay.
just edited the size. Okay,
Okay,
thanks.
Yeah. Tautologies. So there's the one we wrote over here. And then here's another one. P implies Q, and P, this whole thing implies Q. Okay, so if P then Q is true, and if P is true, then Q has to be true. Here's another one. P implies P or Q. And P and Q implies P. So these are kind of, if you want, you can check these using a truth table. But these are really, basic enough that that everybody has an intuitive understanding of them. And these are examples of tautologies, and we'll be coming back to them later. And the reason I want to introduce this in the beginning of the lecture is that the idea is, the key idea in math is we will use lots of these, simple tautologies to derive interesting ones. Okay, so that's all I want to say about logical equivalence and tautologies, which was very little. Any questions about that? Okay, so let's move on to item 2, propositional functions and quantifiers. So by the way, this was section 1.3, and this is like 1.4 to 1.5. So what's the motivation for all this? So the motivation is that we want to be able to reason precisely about large collections of objects, right? So we want to be able to say things like, I don't know, every integer is even or odd. And right now we don't have, propositional logic doesn't let us do that, right? Because right now we would have to say something like, well, one, we could try writing a proposition that says this, which would be something like, okay, 1 is even or 1 is odd, and 2 is even or 2 is odd, and ... But you can see that you can't actually write this down, right? Because you have infinitely many objects to consider. So we want to be able to write statements like this in a precise, concise way, and that's that's the reason why we have these propositional functions. So let me define what that is. So a propositional function let me make sure I use exactly the definition of the book. Okay, is a statement containing one or more variables from a domain which becomes a proposition when each of the variables is instantiated. Okay, so this definition rests on these two other important notions of variables and a domain. So let me just show you some examples. So for example, P of X being X is even. This is a propositional function, and the domain here is
Sorry,
the
Professor.
integers. Yes.
What is the last word in the definition? I can't.
Oh,
understand.
instantiated. Sorry. Instantiated.
Okay, thank you.
So this is X is even is not a proposition by itself, right? Because it's not true or false because we don't know what X is. But when you plug in X from this domain, which is the integers, so the domain must be specified. Often it's implicitly specified. Because if we're saying something is even, well, okay, that the domain could be integers or positive integers or something like that. And once you plug in a particular integer, this becomes a proposition, right? Like for example, P of 2 is the statement 2 is even. And this is actually a legitimate proposition. But the first thing is not a proposition, it's a propositional function. And you can have a propositional function with more than one variable. For example, Q x comma y is X is less than Y. And let's again say the domain is the integers. So this applies to pairs of integers. Okay, so now once you have this this idea of propositional functions, so sometimes also called a predicate. So we'll use those terms interchangeably. Then now you can make statements like the one we want, like every integer is even or every integer is odd, with one more ingredient, which is a quantifier. So let me now introduce quantifiers. This is one of the key definitions of the lecture and maybe of the course. So the universal quantification of a propositional function P of X is the statement.
Professor, would you be able to go to the last slide really quick?
Yeah. So by the way, I guess don't feel compelled to copy the notes since we'll be posting them, but yeah. Okay. So the universal quantification of P of X is the statement for every X in the domain, P of X. So for every X in the domain, P of X is true. And this is denoted for all X, P of X. This is a very important notation that we'll be seeing a lot in the course. And the way this is read is this is read as for all x. And this is a legitimate, this is a proposition, okay? Because this is actually something that either is true or not. So for example, for every x, x is even. This is the universal quantification of the propositional function x is even, and the domain is, let's say, the integers. So is this true or false?
False.
False, right? Because there are odd integers. So it's not true that for every integer. Okay. And the complementary operation is the existential quantification. So the existential quantification of a propositional function p of x is the statement there exists an x in the domain such that p of x. So for example, and okay, and of course there's a notation for this which I'll write down. So denoted there exists x p of x. And this is read there as there exists. There exists x, and sometimes in here you say such that. So the corresponding example, the existential quantification of the same statement would be there exists x, such that x is even. And again, the domain is the integers in this statement. And is this true or false?
True.
Yeah, because there is, for example, 2 is an integer. And so the beauty of this construction is you have a finite statement that actually says something about all the integers. And this is kind of the power of math. You can prove these finite statements that actually say something about infinitely many situations. And okay, maybe let's look at a more interesting example. Here's another example. There exists an x, so that x squared equals 2. And again, the domain is the integers. Is this true or false?
False.
False. There's no integers, so that it square equals this. It squares 2. On the other hand, if I look at the same statement, but the domain I'm interested in is the real numbers,
Then true.
then this is true. So the point I want to make is that the truth or falsehood of a quantified statement depends on the domain. So you must always know what the domain is. Otherwise, it's not clear if it's true or false.
Professor, is it sufficient to just write that it's an element of the integer set or the real number set instead of writing it on the side?
That's a great question. Can we write there exists an x in the integer set such that x squared equals 2? And the answer is yes. And we will do that starting next week. We just haven't introduced set notation yet. And that's not a prerequisite for the class. But we'll start doing that next week. But in the meantime, here's a sort of interesting remark. If you don't want to write the domain, if you want to be really explicit about the domain, you could also specify domain using a conjunction. So for example, you could say there exists an x so that x is an integer and x squared equals 2. So, and in the meantime, you can do that as well. Or you could say, okay, for every x, x is an integer implies x is even.
I have a question.
Mhm.
So, would a universal quantification or an existential quantification be considered as a propositional function or as a proposition?
Right. So once you quantify a propositional function, then there's a legitimate proposition. It becomes a proposition because it's either true or false. So
Mhm.
once all the variables, so actually I should make a sort of explicit point about this. So a variable which appears in a quantifier is called bound. So, I mean, okay, for example, if we if we look at the statement above, right? Then the bound refers to the fact that this x is the same as this x, and the same as actually all occurrences of x appearing in here. So maybe they'll use red to indicate that I'm talking about this arrow. This x refers to all the x's in here. Okay, and that's what turns the propositional function into a proposition. Right? So before, without the quantifier, it wasn't true or false because we didn't know what x was, right? Once you add the quantifier, it's making it very clear which x we're considering, right? So the universal quantification is saying that it has to be true for every x in the domain. And the existential quantification is saying there is at least one x such that it's true. And now there's no ambiguity. That's either it's true or false. Okay. So to answer your question, a statement in which all variables are bound is a proposition. Otherwise, it isn't, right? If you have a variable that's not bound, then, well, the truth or falsehood of the proposition can depend on the value of the variable. Okay. So we're going to look at a bunch of more examples, but any questions so far? Okay. So now I want to talk about how these quantifiers interact with the logical operators, so not, or, and, that we discussed earlier, and also how they interact with each other. So let me begin by talking about negation. Sorry, I think someone is maybe needs to unmute, needs to mute themselves. Okay. Okay, so let me start with an example. So let's consider the statement that let's see what statement. Yeah, how about this? So let's consider the statement every integer is prime. Okay, so that in this language of propositional logic, that's the statement for every x, x is prime, and the domain is integers. Now, what's the negation of this statement? Well, in English, what's the The negation is, well, it's not the case that every integer is prime. But what's another way to say that that's a little bit more concrete?
There is an integer that is not prime.
There is an integer that's not prime. There is an integer that's composite, I guess, is the opposite of being prime. And you know, that statement is there exists an X such that the negation of this is true. Right? There exists an X such that X is not prime. And so the sort of general pattern here which is very important to remember and very useful, is that the negation of a universally quantified statement is an existentially quantified statement. And the negation of an existentially quantified statement is a universally quantified statement. Okay, so this is an important sort of logical maneuver that occurs a lot. Sometimes this is referred to as De Morgan's laws for quantified statements. And the way to remember it is, well, when you negate a quantified statement, you flip the quantifiers, right? So the way to remember it is that the not flips the quantifiers. It turns for all into exists and exists into for all. And okay, this De Morgan, I guess maybe it was in the reading, but let me just remind you that De Morgan's laws, just the vanilla De Morgan's laws, refers to a set of tautologies, which I could add to this simple list here. And those are that the negation of P or Q is negation of P and negation of Q. And the negation of P and Q is negation of P or negation of Q. These are called De Morgan's laws.
Professor, could you go back one slide real quick?
By back, you mean back to here?
Yes, thank you.
So I see that a number of people raise their hands, so please just unmute and ask.
How would you prove De Morgan's laws for quantifiers?
That's a great question. So we will get to that. We'll develop. It's a really great question. How would you prove this? And the answer is we'll use rules of inference, which are something we'll develop at the end of the lecture. So it's a really good question, because if you go back to these sort of vanilla De Morgan's laws, how would you prove this? Anybody know?
Truth tables?
Yeah, you can check using truth tables. But these De Morgan's laws for quantifiers, not so easy, right? Because, I mean, what's the truth table now? There could be infinitely many X, right? So how do you check a statement like this? And that's exactly where rules of inference are going to come in. And I guess I should make one more remark. So I used this notation of logically equivalent, right? Now, previously, I only defined that for compound propositions, but now I'm using it to talk about these statements that have quantifiers and propositional functions. So what does that mean? Well, so I'll just write the definition here. So two statements involving quantifiers are logically equivalent if they have the same truth value for all values of the propositional functions of the propositional variables and all domains for which the quantifiers make sense. Okay, so logical equivalence. So this statement that's written here is very strong. It means that it doesn't matter what domain you're talking about. This always works. It doesn't depend on the domain. So any questions about negation of quantifiers?
Can we go over the last remark one more time, please?
Yeah, so the last remark is actually, let me just make it a definition, actually. It's a definition of this notion of logical equivalence of two propositions that could involve quantifiers, right? Like what's written in this blue box. And the claim is that, two such propositions are logically equivalent if they have the same truth value, regardless of which domain the quantifiers are over. Right. So before we had a few statements, or even here, right? We have the statement up at the top of the slide, and it has different interpretations depending on the domain, right? If the domain is integers, it means one thing. If it's real numbers, it means something else. Logical equivalence is a very strong definition which says that two statements are logically equivalent if they always have the truth value, doesn't matter which domain you use. So these are equivalent in a very strong sense.
Does bijection diverge from logical equivalence in this way?
Yeah, so we haven't defined bijection yet, but bijection is something having to do with functions. This is not something that has to do with functions. This is something that has to do with propositions.
Thank
you. Mm-hmm.
Hey, Professor, can you just scroll quick to some simple but useful tautologies? I just didn't catch the De Morgan.
Oh, sure, yeah. So simple but useful tautologies. De Morgan's laws are saying, well, the negation of P or Q is the negation of P and the negation of Q. So,
oh, thank you. I just needed the last one.
Yeah. Okay. Okay. So somebody asked this great question: how do we establish these? We'll get to this at the end of the lecture, hopefully, if we have time. Okay. So negation is one sort of subtle, interesting thing that happens with quantifiers. An even more subtle thing is what happens when you have multiple quantifiers. Okay, so nesting of quantifiers. So what do I mean by nesting? So what I mean is I can have multiple variables and have multiple quantifiers, right? So for example, let's consider the following statement. For every x, for every y, x plus y equals y plus x. And let's assume the domain is integers. Okay. Now, if you unpack this, what is this really saying in English? It's saying, well, for every integer x, something happens, right? And that something that happens is this whole thing, which is itself a propositional function. So if this was the propositional function q of xy, because it depends on two variables, this is a different propositional function p that depends only on x. Why does it depend only on X? Well, I mean, Y is bound, right? So it's very, so if you plug in the value of X, this becomes a proposition. So this is a propositional function that only depends on X. You don't need to plug in a value of Y because that's included in the definition of P of X. So this is saying for every integer X, for every integer Y, or, you know, maybe just to clarify, say it is the case that for every integer Y, X plus Y equals Y plus X. So you can stack these things together. Now, when you do this, you can do this with existential quantifier as well. You can so by the way, so what fact is this expressing? It's expressing that addition of integers is commutative, that the order in which you add things doesn't matter. So it's expressing a kind of important but basic fact about arithmetic. And yes?
Would you have to specify, would you not need to specify the domain for both the variables in the quantify, like in the nested?
Absolutely. So by integers, I just mean integers for both. So you would have to specify for both.
Thank you.
And you know, similarly, there are some. So one nice feature that happens when you have multiple universal quantifiers is that you can switch the order for all X, for all Y, P of X, Y, or let's call it Q since that's what it was called here, is the same as for all Y, for all X, Q of X, Y. And again, we won't belabor how to establish this for now, although you'll see some techniques how to do it at the end of the lecture, but it's simple enough that we'll just treat it as self-evident for now. Okay. And you can do the same thing for existential quantifiers. So for example, we can do, here's an interesting one. There exists an X and there exists a Y. There exists an X such that there exists a Y, such that let's see, what do I, what example do I want to do? Well, okay, let's do this. X squared plus Y squared equals 0. And again, over integers. So what's that saying? It's saying that there are two integers. There's a pair of integers so that the sum of their squares is 0. So by the way, is that true or false?
It's
Um,
true.
0, 0.
True. It's true because of 0, 0, right? It's true because consider X equals Y equals 0. And this is the same again logically as if you switch the quantifiers. So maybe yeah. And again, that's because if you switch the order, you're still looking for a pair, and it doesn't matter what order you write it in. Now, the more interesting thing happens when you have an existential quantifier and a universal quantifier in the same statement. So the more subtle thing is, let's again look at an example. So the example is, let's do this here. For every X, there exists a Y, so that Y equals X squared. again over integers. Okay. So what is this saying? Can somebody say what it's saying in words?
For all x, there exists a y where x squared equals y along the
Yeah.
range of integers.
For every integer, there's some other integer that's equal to its square. Is that true?
No, that's false.
Well,
Yeah, it's true.
Every
for
integer
every
has
integer x,
an integer square.
yeah, there is an integer
Oh, yes, that's true.
y such that y equals x squared. And we'll talk a little bit more towards the end of the lecture how to like, prove something like this. But in this case, the English sentence is true. If you, for every integer. So first of all, notice that it's actually hard. It's a little tricky to even conceptualize what the statement means. And this is one of the key difficulties in getting to higher level math, that you have a lot of statements with alternating quantifiers. And that's something you'll learn more through practice. But yeah, this is saying for every number, there's some other number that's equal to its square. Well, the answer is, yeah, there is. You just take your x and square it. And then now you have a number y that's equal to its square. However, this is not the same as, or let me say versus, if you just flip the order, there exists a y such that for all x, y equals x squared. This is saying there exists an integer y, just one integer, such that for every other integer x squared is equal to y. Okay, so it's saying that there's one number such that for every other number, when you square it, you get that first number. Is that true?
False.
No, that's false, right? So this is true, this is false. So these are not the same in general. So if you have two different quantifiers, you can't just switch the order. Okay. And okay, maybe this was a little tricky because it was sort of about numbers. Just to make this clear, since this is a very important point, let me show you one more example. The example is, let's see, how do I want to do this? Yeah, okay. For every x, so now the domain is people in this class. So statement is for every person in this class, there exists another person in this class, so that person is strictly taller than x. So this is saying for everybody in this class, there's a person who is taller than them. Is that true?
No, that would be false because there's a tallest person.
Yeah, this is false because there's a tallest person, right? On the other hand, if you write this statement that there exists a person such that for every person x, y is strictly taller than x. So it's saying there is one person who is strictly taller than everybody else. Actually, okay. This is
Isn't this maybe true?
Yeah, this is also false, actually. Okay, maybe this wasn't a good example. This is also false, actually. Why is this false?
Is it because both y and x are taken from the same domain, so you'd be comparing the same person to themselves?
Yeah, the person can't be strictly taller than themselves. So let's, okay, fine. Maybe, so maybe I should, here, let's fix this example. Let's say the statement is there exists, for every x, there exists a y, so that x is equal to y or. So that'll fix this, right? Or, okay. So now this is actually making sense that the first statement is, well, for every person, there is a person who's either equal to them or strictly taller than them. Actually, no, sorry, that messes it up, because for every person there is a person equal to them. Okay, fine. Okay, let's just leave these as false. Maybe this wasn't a good example, but you can see that the meaning of these statements is different, that they're false for different reasons. So the general point I want to emphasize here is that you can't switch the order in general. So any questions about this?
Why is the second one false again?
Well, so the second one is false because let's say I took y to be the tallest person, right? Then I need that for every person in the class, including y themselves, y has to be strictly taller than them. But a person is not strictly taller than themselves, right?
Yes, understood. Thank you. Mhm.
So maybe that wasn't such a great example, but you can see that the meanings of the statements are different.
So the point that you're trying to demonstrate here is that if there's mixed quantifiers, they can't be switched, and we say that they're logically equivalent. They might not be.
They might not be, exactly. So it may not, so if they're all the same quantifier, you can switch them. There's no problem. But if they're different quantifiers, you have to be very careful about the order. The first example is really the good one. The second one is maybe not such a great example because they both ended up being false. But anyway.
Professor, I'm sorry, but I still kind of don't understand the first part, the first proposition.
You mean the one about the square?
No, the y is strictly taller than x. For all x, there exists a y.
Right. So the statement is saying that for every person in this class, there is a person in this class who's strictly taller than them.
And the reason that's false is because y is the tallest person.
Well, the reason is that what if you take x to be the tallest person? Then there's nobody strictly taller than them, right? So it's false.
Oh, okay. Thank you. Yeah. Thank you.
Yeah, I mean, maybe this wasn't such a good example because it's kind of false for. I mean, okay. Let's try to salvage this.
Could you
We
say
changed
that for every
correctly.
x not?
Oh,
Sorry.
you first.
Could you say that for every x not equal to y for the second statement, and then it would be true because it would be for everybody except himself.
Okay. So you could so basically you're saying that Well, I want the same statement, I guess, in this example. So you're saying that here x not equal to y implies y is strictly taller than x.
Yeah, like even the quantifier outside, right? Like if there exists a y that for every x not equal to y is strictly taller than x within the room.
Okay. Yeah, I mean, the reason this is getting tricky is I wanted to have the same statement above, and then this is going to significantly change the meaning of that statement. So maybe let's just leave this example for now as a indication of how I guess how quickly the meaning can change by changing, adding words like strictly. Okay. So one let me do one more example. So in particular, if you combine what we learned about nesting and about negation, you get that the negation of there exists x such that for all y q of xy. So what's the negation of that going to be? Well, by De Morgan, this is going to be for all x, the negation of for all y q of xy. And then by De Morgan again, this is going to be for all x, there exists y such that the negation of xy. Okay, so if you negate a statement with multiple quantifiers, it still flips the quantifiers. It just sort of passes through or flips them one by one. Okay. Don't worry about this. We're going to get tons and tons of practice with this in the semester. It's really something that's going to come up almost in every class or every lecture.
I'm sorry, I have a question about
Mhm.
this part really quick. In the last line, because for every y in the negation part in front of it, that changes it into that last line. Oh, okay, got it. Thank you.
I just applied this De Morgan for quantifiers twice.
Yeah, I see. Thank you.
Okay. And there are many interesting examples of statements that involve multiple quantifiers. Let me just give another one. Another one that I like is for every x, there exists a y, so that if x is not equal to 0, then xy equals 1. And the domain is real numbers. So what fact is this expressing?
Every number has an inverse.
Every number that's not 0 has an inverse. If x is, for every real number, there exists another real number y, so that if x is not 0, then x times y equals 1. And that number is 1 over x. And what's the negation of this? Well, the negation of this is that there exists a real number such that for every y, the negation of this conditional holds. Okay. And well, so what's the negation of a conditional? Anybody see how to write that down? We'll make a little box here. What's the negation of P implies Q?
For every x, there is not an inverse. Why?
Is it? No, never mind.
Okay, just a second. Okay, this is really annoying. I thought I've changed my graphics drivers, hoping not to have this problem again. But let me. It looks like I'm having this problem with the colors again. So let me fix it.
Professor, I think you're muted.
Oh, sorry. Yeah, I was saying, well, I guess we got a little break out of it, which is not so bad for a long class. So, okay, so let me now get to the third part, which is rules of inference. Can you see this? Okay. So,
Yes.
As I was saying, we've been talking about how to write statements with a precise meaning and truth value. And now we're going to talk about how to write arguments which establish the truth values of statements that we would of new statements. So basically how to prove new statements. And so the key device for doing this is what's called a rule of inference. Let me start with an example. So here's an example. Here's one proposition. It is if it is raining, the dog is wet. And here's another statement. It is raining. So now, intuitively, we make this argument all the time. We can conclude that the dog is wet. But what is actually the logical device behind this deduction? Well, it's actually a tautology. So let's say it is raining is the proposition R, and the dog is wet is the proposition W. Then the first proposition is R implies W. The second proposition is R, and the conclusion is W. Now, this was actually one of the sort of simple, easy tautologies on the second slide of this lecture, if you recall. Okay, so what was the reasoning process here? Well, this was what we really used here is the tautology. R implies W, and and R implies W. Okay, and this has a fancy Latin name. It's called modus ponens or something, which I can never remember, and you don't have to memorize these names. But the key point is that this little tautology is what enabled us to do this reasoning. And you have slightly more complicated examples of that, like, okay, if it is raining, the dog is wet, so that's just R implies S again. And then the dog is not wet. Then you conclude that it is not raining. Right, so this is not W, and this is not S, this is W. And then this is not R, right? But how do you actually make this deduction? Well, again, behind this, there is a tautology. The tautology is that, okay, P implies Q, or in this case, R implies W, and not W implies not R. This is also a tautology. This also has some Latin name. I don't remember what it's called. But the point is that inference, logical inference, is really driven by tautologies. It's driven by these little obvious statements. And there's, you know, a list of the most common ones that you can view in the book here. So here's the book. If you go to section 1.6, there's a table of rules of inference. And these are basically, you know, many of them are the little simple tautologies we wrote at the beginning of the lecture. They can all be easily verified, and they all have complicated Latin names which you don't need to know. Okay. And so these are what are called rules of inference for propositional logic. They're just these baby tautologies that you stitch together to reach new true propositions given some propositions you already know to be true. So let me, I guess, just formally define this. So reasoning is driven by these sort of useful tautologies. And yeah, let me just use the definition. So definition. So rules of inference are just useful tautologies. Used to derive, well, true propositions from some, okay, to derive from some known true propositions. And okay, this definition is not really important. The definition that is important is, which actually has a mathematical meaning, is an argument. So an argument is a sequence of statements in the sense of propositional logic, and the last of which is called a conclusion. And the argument is valid if each statement follows from the previous ones and some rules of inference. The previous ones and rules of inference. Okay, so if you just have a sequence of statements, but they don't have the structure, it's not a valid argument. It's an invalid argument. And so a valid argument is a bunch of baby steps namely these tautologies connecting a sequence of propositions. So let me give you an example of an interesting valid argument. Yeah, okay, for example. Yeah, okay. So here's an argument proving that the following is true. P and Q implies P or Q. So this is a tautology. Okay, so what's the argument? Well, I have that P and Q implies P. So that's a tautology. That's already a rule of inference. And I have, I believe this is called, this has a name. It doesn't matter, but it's kind of obvious. Then I have P implies P or Q. This is also a tautology. And now I can chain these together to get that P and Q implies P or Q. I think this is called hypothetical syllogism, which is just another tautology. So I have three statements, and the structure is that the first two are tautologies, and the third one follows by combining the first two. And let's say this is the conclusion. Okay. And I should say an argument often starts by assuming a collection of statements which are called premises. So in this case, there are no premises. Everything is a tautology. Okay. Let's do a more interesting example. This one was kind of basic. So what's more interesting is a rules of inference for quantifiers. Okay, so there are four rules of inference for quantifiers. So one is that the statement for all x p of x implies p of c for arbitrary c in the domain. Okay, so an example of this is so for example, let's say an example. So this is called universal instantiation. You don't need to know the names. And an example of this universal instantiation is, well, for every human x is mortal. And this implies that, let's say, Nikhil is mortal. But you could plug in anybody here, anybody who's a human. And the reverse of this is what's called universal generalization. And what that says is that if you can show that for an arbitrary element of the domain, a certain propositional function holds, that implies that the quantified statement for all x p of x is true. So an example of universal generalization is, let's say I say assume, well, I mean, okay, maybe this, maybe I'll leave this example for a little later, actually. And then there are some similar rules of inference for the existential quantifier. So the statement, there exists x so that p of x. This implies, so this is existential instantiation. This implies that p of c is true for some c in the domain. So what that means is that if you know that the statement written above is true, then there must be some one point in the, I mean, it's almost a definition of the existential quantifier. There must be some element in the domain for which that statement holds. And this is called existential generalization. So this is sort of a subtle concept. Let me give an example of existential generalization. Let's say I just have that Nikhil is mortal. What can I conclude from that? I can conclude that there exists a human so that the human is mortal, right? Because Nikhil is a human. So I mean, okay, the implicit domain in all these examples is humans, right? Or yeah, mortal means will die, and human means human being. Now, this might seem like kind of just a word game, but the content of this is what's written above is a proposition with a quantifier, right? And for example, over here, there's no particular element of the domain that's being considered. It's just a statement about the domain at large. So what universal instantiation is saying is that if you know something is true for every element of the domain, you can choose an arbitrary element of the domain, and then you know that statement is true for that element. So, okay, let me do one example illustrating. I'll do a classical sort of example from a couple of 100 years ago, illustrating how these are used in writing a proof. So this example is due to Lewis Carroll, who wrote Alice in Wonderland and was also a mathematician whose interests were logic and linear algebra. And so here's an informal argument. The argument is all lions are fierce. Some lions don't drink coffee. Therefore, some fierce creatures don't drink coffee. Now, how do we turn this into a formal argument that uses these rules of inference? So let me demonstrate that. So first, let's define some propositional functions. So L of x is a lion. F of x is fierce. And C of x is x drinks coffee. And the domain for all of these is, let's say, all living creatures. So informally, what do these statements refer to? Well, the first statement is saying for every x, for every creature, if it's a lion, then it's fierce. L of x implies f of x.
The second statement is that there is an x such that x is a lion and
exactly
not x drinks coffee.
Exactly. So there exists a creature so that creature is a lion and it doesn't drink coffee. And then the goal.
The third statement is there is x such that x is fierce and x does not drink coffee, or not x drinks coffee.
Yeah, not C of x. So we want to conclude the third from the first two, but how do we do that, right? Like the same seems to make sense, but let's do it formally. So again, I'll take 1 extra minute. I'll write down all the steps in this formal argument. Okay. So let's do the formal argument, right? Okay. So all lions are fierce. That's a premise. So for all x, L of x implies f of x. That's a premise. Now, actually, sorry, I don't want to write that first. Sorry. So what am I going to do? I'm going to start with the second premise. Some lions don't drink coffee. So there exists an X so that it's a lion and doesn't drink coffee. That's a premise. Number 2. Now I'm going to use existential instantiation to say, hey, this implies that there has to be some particular lion that doesn't drink coffee. Right? So this means L of, let's just call it, let's just call it A, and not C of A for some particular A. And here I used existential instantiation. And so the benefit, so when I write proof, I always have this metaphor of a table in the background. And what the table has on it is some particular objects, which are bound, usually come from being bound variables with a quantifier. So now there's a creature on the table, which is a lion, and it doesn't drink coffee. Right? Okay. Now, L of A and not C of A, well, this implies that just L of A. Why? This is because P and Q implies P. That's one of those rules of inference, right? Okay. But now I have another premise that all lions are fierce, right? So I have that for all X, L of X implies F of X. This is premise number 1. This is saying something about all creatures. But now I can apply it to, remember, universal instantiation means I can apply it to any element of the domain. So in particular, I can apply it to this lion A that's sitting on the table. So this implies L of A implies F of A. This is universal for the A that I have on the table, this is universal instantiation. Okay. Now, if I combine statements, let's give these names. If I combine statement star and statement double star, then I get that F of A, right? Because, I mean, that's just modus ponens, actually, right? But now I have on the table F of A, and I also have C of A. Sorry, not C of A. And I have that because I have from the second statement, L of A and not C of A. And so then I have the AND of those, F of A and not C of A. And now by existential generalization, I get that there exists an X, so that F of X and not C of X. This is existential generalization. Okay, so that was an example of how you use these rules of inference to prove something, right? To formalize this argument. And we're going to do a lot more of this in the next lecture. The main thing I want to introduce is this metaphor of this table, that these quantifiers allow you to put things on the table, and then you have specific objects instead of having to think about this whole universal object as a whole, objects at once. Anyway, really sorry for the technical difficulties again. I don't know, I'll find some way around it for next time. But thanks.
Thank you.
Thank you. Thank you.
Thank you.
Thank you.
Thank
Bye.
Thank you.
Great evening.
Thank you.
I wanted to ask, in what situations would you use equal to t and the compound proposition the compound proposition with T?
The compound proposition, which compound proposition?
If you're saying that something is true, would you say, in what cases would you use equal to T, and in what cases would you
Okay,
use
I see, yeah. So you're right. So implicitly, what I'm writing here is I'm writing a sequence of true statements, right? So this is a valid argument because each statement is either a premise, which is something that was given to me, or it follows from the previous statement by applying a rule of inference. So implicitly, what I'm saying here is actually that all these statements are true. And I guess you're asking, why am I not saying so-and-so is true, right?
Yeah. It seems like you use different ones for different situations. Like if you have a, if you have a statement versus a proposition, but I can't entirely tell when you do use it, when you do and don't use it.
Okay, so there is true. So let's see. I haven't been using it recently. I used it in the knights and knaves situation, right? And part of the reason for that is that I was actually doing something a little bit different there. I was trying to find out if there is an assignment of truth values which makes certain propositions true. What I'm doing here is a little bit different. What I'm doing here is I'm saying, hey, here are two propositions that I know are true. Can I use those to deduce some other proposition? So basically, I'm not writing it here because it would be redundant. That I'm not writing any statements that are false here.
Yeah.
I'm staying in the realm of true statements. And when you write a proof, yeah, it's implicitly assumed that whatever you are writing is true, unless you're writing kind of a, a meta statement, which is about another statement and saying that that's false or something like that. Does that answer the question?
Kind of. Can I type something out?
Sure.